Yesterday I published a circuit made with this chip here. It is the NA5532 chip. And well, my idea was let me try to use that chip to make a sine wave, not a square wave, but a sine wave. And of course, when you know a little bit about electronics, you will surely know that you can change a square wave into a sine wave with a very simple filter consisting of a few resistors and a few capacitors. And that is here. So this is a conversion from a square wave into a sine wave, and I've used that also in this case. And of course you know that is frequency dependent. When you go to the World Wide Web, Google, etc., you can find many say circuits where this is all calculated. But when you do experiments, there are a few things to know at first about the resistors here and about the capacitors, and this is say a kind of general information. The resistors can be in transistor circuits, by the way, between 500 ohms and 5 kilo ohms. The capacitors are in the range of 1 nanofarad, that is 1000 picofarad, and 100 nanofarad. And of course, when you know a little bit about, say, the theory, these capacitors have to have a higher value when the frequency that is sent into that filter is lower. So say on let's give it a try on 10,000 hertz, that is 10 kilohertz. These resistors could be 1K and the capacitors could be in the order of 15 nanofarad or 10 nanofarad. And when you go to much lower frequencies, say in the order of 100 hertz, 200 hertz, perhaps 800 hertz, the capacitors have to be in the order of 100 nanofarad, that is 0.1 microfarad. Anyway, I don't elaborate more. Do your own experiments. I can only say a few first things about that filter. And when you study this schematic here, it's made with 2 times the NA5532. You also see here that filter. Resistor, capacitor, resistor, capacitor, and the interesting thing is that here the signal gets in, that is say a square wave, and slowly it changes over the filter into a sine wave. And because we are now working on a quite high frequency, say between 150 kilocycles and 400 kilocycles, the filter capacitors have to be small. Anyway, so let me give a demonstration about how this circuit works. In fact, it is relied to the earlier circuit where, say, a square wave was made, and here when you study that on the scope, here you see a square wave, and here you also see a square wave on this location, but here you see a sine wave, and here you see a kind of triangle wave. That's in a certain way a problem, but anyway, Here is a circuit on the breadboard, kind of breadboard, say not the common breadboard. Here is the tuning capacitor that goes from 5 picofarad up to say 60 picofarad, and I have made a switch here, and with that switch we can give that capacitor somewhat more capacitance, and that is 100 picofarad. The first op-amp, second op-amp, I had to change the, say, on pin 3 I had to change the values of these two resistors. They set in a certain way a kind of voltage here, and make that this circuit can work on only one voltage, so I don't need a double voltage supply. And that's more or less, say, the reason why you see it here. 1K, that works good, and here you see exactly the same, by the way, but now it is 100K here and 100K here. When you know a little bit about electronics and op-amps, you will surely understand how that works. So I was panning over. Here is the capacitor that sets the frequency, and now we are on 188 kilohertz, kilocycles. Waveform is pure. I had to do quite a few experiments to get it as pure as possible, but anyway, has to do with the 3-pole filter or 2-pole filter. That's perhaps interesting to tell. Say, you can also derive here a sine wave, but it is somewhat distorted, and here it is less distorted, etc., etc. And here's an amplifier. It took some time to figure it out, and here is 1 nanofarad and 1 M5 resistor that compensates the, say, the amplification, and makes that the waveform is pure anyway. So here we have again that waveform, 188 kilohertz. I'm now tuning the capacitor, and of course with smaller capacitances we get to higher frequencies. Take some time, so move the plates a little bit. Let's go to the highest frequency that it can give, and that's approximately when the capacitance is too low, the oscillator doesn't work. That's perhaps important to tell, but here we have, say, the highest frequency. In this case it gives a sine wave, and it works on 379 kilohertz. And that's not bad. And of course we have to do with, in a certain way, the problem that the amplitude changes when you tune to a certain frequency. Anyway, not always logical, but in this case somewhat logical. See, I turn it a little bit back, and here you see the amplitude changes. So on the lowest, not lowest anyway, but the lowest frequency, 189 kilohertz, it's the maximum amplitude, and on the somewhat highest frequency we have a much smaller amplitude, and it is on 345 kilohertz. I've also made here a switch, and with that switch you can, say, bridge the tuning capacitor to another value, 100 picofarad. Let me do it. It's the switches here. And in that case we are going to other frequencies, of course, completely logical when we look at the radio theory. And now we are on 164 kilohertz. And now I turn the capacitor back. It means we give the oscillator a higher input capacitance, and it means that the frequency goes down. 153 kilohertz. So let me show again, try to show again what happens when you switch that extra capacitor in. So waveform is quite pure. I did a lot of experiments to get it as pure as possible. So let's look at the schematic again. I always had in the past a request to show the schematics for a quite long time, so I did it and do it now. And in fact, we have here a square wave oscillator. Here is the filter that changes the square waves into sine waves, and here is the amplifier. I've used, by the way, a normal standard transistor, the BC547B, and to cure the waveform a little bit, I have used this here, a 1 nano capacitor bridge with a 1 mega ohm, 1.5 mega ohm resistor between the collector and the base, and say that is in a certain way a classical way to say cure waveforms, make waveforms better, give it a better figure. I mean the shape of the wave, because sometimes inside such a transistor there is not enough capacitance to say give that good waveform out. So this is pure experimental. There is of course inside such a transistor there are natural capacitances, and when they are too small the transistor sometimes cannot work properly, and especially on these higher frequencies. So that was more or less all to tell. Thanks for watching. I think it's a very useful circuit. It's easy to make. The only problem is, but that does not have to be a problem, because it has everything to do about the way that you want to use this circuit, is that the amplitude changes when we go to the higher frequencies. Pen over somewhat. Here is that amplifier. It has to amplify the weakened square wave, and here are the two op-amps that do the job, and here is the frequency dependent capacitor, and here is again that filter that is necessary to make the circuit stable. Well, that was more or less all to tell. I only have 1 minute on my camera. Thanks for watching. So I only pen over somewhat. Here I've used a 47K potentiometer to make the whole circuit low impedance. Here, etc.